Hello students, it's your professor Dr. Mink. Welcome to another fun and exciting lecture. In this lecture we're going to cover the LC3 and we're going to dive into the deep end of the machine language and assembly language pool. Let's get started. Let me reintroduce one of the key terms of this class, instruction set architecture. Abbreviated ISA. It is all the programmer visible components and operations of the computer. The memory organization, the address space, how many locations can be addressed, the addressability and or architecture size, also called the bus size, how many bits per location. The LC3 is a 16-bit instruction set architecture. The register set, how many, what size, how are they used, and then the instruction set, the opcodes, data types, and addressing modes. The instruction set architecture provides all the information needed for someone that wants to write a program in machine language or translate it from a high-level language to machine language. The LC3 has an address space of 2 to the 16th locations, and each one of those memory addresses is 16 bits, thus the addressability. It's a 16-bit instruction set architecture. There are 8 registers. Registers are temporary storage locations accessed in a single machine cycle. They are right there in the processor. Accessing memory takes longer than a single machine cycle. So the more registers you have, the quicker you can handle processing. The 8 general purpose registers, R0 to R7, obviously 16 bits wide. How many bits do we need to uniquely identify 8 registers? 2 to the third is 8, so we need 3 bits. We have some other registers that are not directly addressable but used and affected by the instructions we're going to be processing, the program counter, and the condition codes, etc., that we will drill down on in significant detail. The opcodes, as we've seen already, are 4 bits. We actually can support 16 opcodes, but currently we're only using 15 in the LC3, and they fall into the 3 categories of operate, data movement, and control. Some of the opcodes set or clear condition codes based on the results. And those are only opcodes that assert the write enable signal for a register. In other words, they write a value or store a value in a register. And just hold that thought, because when we see the instruction set in a few minutes, you'll see a plus next to some of the instructions, and those are the ones that set the condition code. The condition code is one of 3 values: N negative, Z 0, or P positive, and that's based upon the sign, negative, 0, or positive, of the last value written to a register. Data types, 16-bit, 2's complement integers. Addressing mode has a location of an operand specified. We're going to get to that. Non-memory addresses, immediate versus register. Memory addresses, PC relative, indirect, and base plus offset. All of these are going to be covered in significant detail. Here is the memory map, addressed in hexadecimal. So you see X0000, that is the first address of the first memory location. And hex FFFF, you'll see the X, that just means it's hexadecimal notation. FFFF is the last memory address in the LC3 memory map. you'll see, and there's various sectors or areas of memory that are designated for specific operations or parts of the LC3. The trap vector table, the interrupt vector table, the operating system and the supervisor stack, and then we have hex 3000 to FDFF. That is the space in the memory map available for user programs. And you're going to see, I think you've already seen one or two programs that I've written. You're going to see a lot of programs have an origin statement of hex 3000. That's the first available memory location for user content. Doesn't have to be hex 3000. And then we have the device register addresses FE00 to FFFF. And like I mentioned, every single part of this memory map will be covered in significant detail. And you'll understand what a trap vector table is, what the interrupt vector table is, operating system, supervisor stack, and the device register addresses. They will all be covered in very, very significant detail as we move forward through the course. This is the first page of 2 for table A.1, notational conventions. And 2 slides forward, you're going to see the instruction set. And each of these notations, which is listed in the first column and then described in the second column, is used in that map. You're going to have to understand what each of these notations means with regard to the instruction set and the syntax of the instruction set, both in assembly and machine language. So, for example, when you see X followed by a number, that's the number in hexadecimal notation. If you see pound followed by a number, that is the number in decimal notation. And each of these can be used interchangeably in the assembly language mnemonics. A bracket L colon R means the field delimited by bit L on the left and bit R on the right. Example, PC contains certain bit pattern, then PC 15 colon 9 is bits 15 through 9 inclusively. Base R is base register, one of R0 through R7, use it in conjunction with the 6-bit offset to compute a base plus offset address. DR stands for destination register, IMM5, 5-bit immediate, 2's complement, sign extended value. Label, we're going to get into labels later. Label is a construct of a programming language, and assembly language includes labels. And then mem, and then brackets, address denotes the contents of memory at the given address. Offset 6 is a 6-bit value used with the base plus offset addressing mode. PC stands for the program counter. PC offset 9 is a 9-bit 2's complement, sign extended, offset used with the PC plus offset addressing mode. And PC offset 11 is an 11-bit 2's complement, sign extended offset used with the JSR opcode, jump to subroutine. Continuing through table A.1, PSR, processor status register, 16-bit register contains a status information of the processor that's running, privilege mode, condition codes, etc. When we get to preserving the state in calling a function, we'll cover PSR. Set CC indicates that the condition codes are set based on the value of the result written to the destination register. SEXTA, sign extend A. The most significant bit of whatever A is replicated as many times as necessary to extend A to 16 bits. So for example, in the immediate mode version of add command where bit 5 is 1, those 5 bits gets sign extended to 16. SP is the stack pointer. We'll get to that. SR, SR1, and SR2 stand for source registers. They're one of the 8 registers. R0 to R7 specifies the register from which a source operand is taken. SSP, the supervisor stack pointer, that's way down the road, but we will get to that. Trap vector 8, that's way down the road also, but we will get to it in very significant detail. It's an 8-bit value embedded in an instruction that's used with the trap opcode. A trap opcode is a system or privileged subroutine. Like I said, way down the road, nothing we have to worry about for several weeks. USP, the user stack pointer, another advanced topic we'll get to. And ZEXTA is zero extend. Zeros are appended to the leftmost bits of A, extending it from whatever it is to 16 bits. So, all of the notational conventions that we just covered are applied here. This is the most important piece of information moving forward. It's going to be the chart you use most frequently the rest of the class. This is the instruction set. This is all 15 instructions for the LC3. And you'll see, well, there's more than 15. Yes, some of the instructions like add and have 2 versions of the same opcode. If you recall, add has a register mode where both of the operands to be added together come from registers, and that's designated by bit 5 being 0. Add also has an immediate mode where source register 1, the contents of whatever register address is in bits 6, 7, and 8, is added to a 5-bit 2's complement sign extended value. That's sign extended to 16. And those bits are 0 through 4. When you see the plus next to the assembler mnemonic, add, and, load, LDI, LDR, LEA, not, those are instructions that set the condition code. Why do they set the condition code? The condition code is based upon the sign of the last value written to a general purpose register. All of those instructions, if you look at the syntax, have a DR, a destination register. That means they store a value to a register. The sign of that value, negative, 0, or positive, sets the NZ or P condition code. We're getting ahead of ourselves, but so this map or this table, the instruction set, is something you're going to use to write both assembly and machine language code. And as I mentioned, we're going to learn assembly and machine language concurrently because there's a one-to-one relationship between an opcode and an assembler instruction mnemonic like add. Add always generates opcode 0001 and always generates opcode 0101. Branch, BR, always generates opcode 0000, etc. So, I don't know. I don't like to print things. When I first started teaching this course many years ago, I did print this thing and carry it around with me while I was writing assembly language and machine language instructions because it had been quite a while since I took this course I took a version in undergraduate and also when I got into grad school, for whatever reason, that didn't transfer as the undergraduate requirement to get into grad school, so I took it again. I took a different version at a different college. So you're going to want to have this handy as we move forward in the class. So let's get started. How do we How do we subtract when we don't have a subtract instruction? We only have add, and not. So if we want to subtract the contents of register 2 from the contents of register 1 and store it in R3, we simply take the complement, the 2's complement of R2, and then add R1. So how do we take the 2's complement of R2? Well, we use not. Not flips the bits, and we add 1. And then we store that back into R2, and then we add R1 and R2, which is the equivalent of R1 plus negative R2. Here we have in the editor, the LC3 editor, we have example 5.2 from page 123 in your textbook. Simple origin statement, which means we're going to start our program at hex 3000. That's not 3000, by the way. That's not hex 3000. That's hex 3000. And we're going to start off by ANDing R6 in itself. Well, what does that do? That's going to clear or 0 R6. Whatever's in there, it will be 0. And so then we're going to add R6 and a #1. What's pound mean? That's a decimal representation of 1. We're going to add 1 to R6. We know R6 is 0 because we started by ANDing it with 0. So this will be add 1 to R6, which is already 0. Okay? And. Okay? Pretty straightforward. If I wanted to, oops, I have to save it. I'm just going to call this EX 5-2.asm. I already have it. It's going to tell me, yeah, I know. And if I were to assemble this, okay, right, and then I could just go right to my, should have my LC3 open, and there's my binary. Open that. And here we have generated 3 lines of machine code. This first is the origin statement. That's hex, see it? 3, 0, 0, 0. And what is this? Well, 0101 is the opcode for AND. R6, our destination register, that's where we're going to store the result of this AND. There's R6. Our first operand is the contents of R6. We've got 1, which means we're in what? Register mode? No, we're in immediate mode. That's a 0. That gets sign extended. So 0 and it with anything is 0. This is the quickest way to clear a register or set it to a known value, 0 being a very convenient known value. And then we're going to add, and the result of this add, the destination register, is R6. The source register number 1 is R6. Bit 5 is 1, which means this is a 5-bit 2's complement sign extended value. That's 1. That gets sign extended to 16 and added to 0 and stored back in R6. Okay. Now, I could show you this running in the simulator, but let's do something a little different. Let's Let's put a value in R6. And we'll put a pound 5. Okay? And then let's take the 2's complement. How do we take the 2's complement? Not R6, comma R6. And then we're going to add 1. Okay? I'll save it. I'll run it. We're going to have the machine language, but let's go right to the simulator. I'll pull up the simulator. Whenever you have the simulator open, you want to restart it, just reinitialize the machine. It zeros everything. Now, File, Load Program. I'm going to load the OBJ. When I assemble this, remember it's a simulator, it creates the machine language and some other things that we're going to cover later, and the OBJ. Here's our program in the simulator. And you could see this is a simulator. You're not going to see this in real life, right? So let's just step into this. First thing we're going to do is 0 R6. There's nothing in R6. Now we're adding 5. R6, right? Now we're going to flip the bits. So we're going to get some weird value in R5. R6. Okay? We got -6 and we're adding 1. There you go. We took the 2's complement by flipping the bits and adding 1. And now we could add that to another value to simulate subtraction. We have 3 operate instructions, arithmetic logic instructions, if you will. They're add, and not. You'd be pleasantly surprised as to how much we can accomplish with add, and not. They're logically complete. Source and destination operands are registers or an immediate value that is hard-coded into the instruction. These 3 instructions do not reference memory. They do not go outside of the processor. As I mentioned, add and can have an immediate mode where one of the operands is hardwired into the instruction. We'll show the data flow diagram with each instruction, and it'll illustrate when and where data moves in order to accomplish the operation being discussed. Remember, not is a unary binary function. Unary, as in unicycle, means 1. There's only one operand. So in this data flow diagram, whatever value, whatever 16-bit value is in the source register, whatever that is hard-coded into the instruction as, that's fed to the arithmetic logic unit, signaled to the not circuitry, and basically wherever there's a 1 it becomes a 0, and wherever there's a 0 it becomes a 1. So it flips the bits, and then it stores the result in the destination register. If you recall the short demo I did a few minutes back in this video, I flipped the bits of R6 and I stored the result back in R6. So the destination register and the source register were both R6. Next, we're going to present the data flow diagram for add and together. Add and in register mode together. Because they, other than the binary operation, the syntax is exactly the same. One adds, one ands. So you can see it is a binary function, meaning there are 2 operands. So the operand from source register number 1 is retrieved, the operand from source register number 2 is retrieved. Signal is sent to an add or AND circuit, depending upon the opcode. And the contents of source register 1, is added or ANDed, depending upon the opcode, with the contents of source register 2, and the result is then stored in the destination register. Pretty straightforward. The data flow diagram of add and AND immediate mode has one extra step, as it's retrieving the second operand for the binary function. Its sign extends bits 0 through 4 to 16, and that will take a machine cycle, and then feeds the second operand to the arithmetic logic unit along with the first operand from source register 1, stores the resultant added or ANDed bit pattern, 16-bit pattern, into the destination register. So, you remember De Morgan's law, distributive property for logic. With only add, and not, how do we subtract? Well, we just showed you how we subtract. We take the second operand, flip the bits and add 1, and we simply add it. How do we OR? How do we copy from one register to another? How do we initialize a register to 0? I think I've already shown you that, but we're going to cover each of these scenarios next. This is review. If we want to subtract R2 from R1, we take the 2's complement of R2, then add 1, and we simply then add them. And it becomes, R2 becomes negative, so we're adding negative R2. Okay. Using De Morgan's law, we can OR R1 and R2 and store the result in R3 by simply inverting R1 and R2, AND them, and then invert the result. So R1 is not R1, R2 equals not R2, R3 equals R1 and R2, and then R3 equals not R3. Pretty straightforward. How do we copy a value from one register to another? In other words, how do we assign the value in R2 to R3? We simply use add with the immediate mode, and we add R2 plus 0, and the destination register becomes R3, and in fact we've moved R2 to R3. How do we initialize a register to 0? We just covered that in the previous couple examples. We simply AND it using the immediate mode of AND with 0. So if we want to 0 R1 or assign 0 to R1, we source register 1, R1, or operand number 2 is an immediate 0, immediate 5-bit 2's complement sign extended value. That's a mouthful. And the 2 and store it back into R1. In addition to arithmetic logic operations, we need to be able to load or move data around, thus the data movement instructions. Load, we read data from memory into the processor in a general purpose register. You should know that memory or the processor never accesses memory directly. Every piece of data that winds up in the processor first has to go through one of the registers. Just the way it is. We have 3 load commands to load data from memory to a register. LD uses the program counter relative mode. LDR, which we've covered already, or we reviewed, I should say, uses the base register with a full 16-bit or 4-bit hexadecimal memory address represented as a 16-bit binary number. plus an offset, or LDI, load indirect. Load indirect is one of the more complex instructions to understand, so we'll get to that. In store, when we're done with data that was processed by the processor and we want to store it to memory, write it from, maybe it was in a destination register from a series of operations, and then we want to get it out so we can use that register for something else. We want to store it in memory. We're going to use one of the store commands. Store, just like load, is PC relative to calculate the target address where we're going to store the value. STR, just like LDR, we have a full 16-bit binary value that represents a 4-bit hex address plus the offset. And then STI works just like LDI, but we're gonna spend a significant amount of time explaining that rather complicated addressing mode. And we also have load effective address. Okay, this does not access memory. Okay, it loads the effective address, and we use a label. So just hold it. We haven't gotten the labels, and you're probably thinking, what the heck is a label? Right. We will get to that, but we're in overview mode now, mile high, and we're going to drill down to the street level later in this presentation. Okay, students, time for a hands-on demo. Now, I really want you to go through this with me. Don't skip it. Here's a program that uses store and load, and we're going to be talking about PC relative addressing mode. So what I'd like you to do is go to Canvas. I've stored the text for this program in a page called SDLD program. Copy and paste it into the editor and follow me on this hands-on demo now. So here I have the editor launched. I have the contents of that program in the clipboard. I just copied and pasted it. And we're going to walk through this, generate the machine language code, import it into the simulator, and run it. So simply, if we want to talk about what's going on here, we're starting at origin hex 3000. We're going to zero out R6, add 1 to R6, then add -16 to R6, and here's the part I want to talk about. Okay, this, we're going to store contents of R6, PC plus 15. So we're going to specify the target address where we're going to store the contents of R6, which is going to be a -15, decimal -15, but it'll store it in binary. 15, we're going to take the value of the program counter and we're going to add 15 to it, and that's going to be the target address for the store. Then we're going to load from an address PC plus 14 into R7. So we're going to go out to memory. We're going to calculate the target address by adding 14 to the program counter and store whatever's there into R7. And that's the end of our program. I'll just call this, I probably already have st-ld.asm. Oh, I don't. Okay. And then I will assemble it. No errors. We'll get to why it takes 2 passes in a few minutes, but there's my simulator. I'm going to reinitialize it. I'm going to load. I'm not worried about going too fast because you can pause this. You can pause this, you can rewind it. There's my STLD. And there's my program. So walk through this with me. I'm going to step into it. We're 0 in R6. We're adding 1 to R6. There's the 1 in R6. Now we're going to add the contents of R6 plus a negative 16. Store it back into R6. There's our negative 15. Now here's the part I want to talk to you about. Now this is a simulator. I wish it didn't do this. It actually calculates the target address over here. But let's talk about this. So the command store R6 15. So what will the program counter, that instruction is at 3003. It's going to calculate the target address by adding 15 to the program counter during the decode, evaluate operands, during the instruction processing cycle. But what happens to the program counter before it gets to that, before it actually executes the command? The program counter gets incremented to 3004. So if I add 15 to 3003, let's do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It would be 3012. But remember, the program counter is already +1. The program counter, when the offset is evaluated, the program counter, because that happens first during the fetch step of the information processing cycle, instruction processing cycle. It's already 3004. That's why this is 15. So watch. Step into this command. There's that value, right? FFF1. That's just a hexadecimal representation of it because we don't have enough landscape up here to put the binary. There is our negative 15 stored at hex 3013. You saw that already because it resolves that here. Now we're going to load into R7. And this command, this instruction is going to be at 3004. But remember, the program counter is going to be at 3005 by the time it evaluates the offset. 3005 and 14. Let's do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's going to calculate the same target address, 3013. It's 14 because it's 1, the program counter is 1 ahead of where it was in the previous instruction. So we're going to load into R7 that value and watch what happens to R7 up here. There it is. That is PC offset addressing mode. Takes the program counter, it adds a value to it, calculates the target address. I strongly urge you to mess around with this program. Change the offsets, make it a little different. What we just demonstrated was PC relative addressing mode. It gives us the ability to specify an address, a target address, directly in the instruction. So an address is 16 bits, and so is an instruction after subtracting 4 bits, blah, blah, blah. Okay? We use this 9-bit in the PC relative addressing mode as a signed offset from the current program counter, right? 9 bits, negative 256 plus 255, right? 2's complement. We can only go plus 255 or minus 256 from the current program counter. If you need to store or load from an address, to or from an address, that is further than 256 memory addresses, memory locations away from the instruction, then you need to use one of the other addressing modes. Maybe designate a base plus base register, which holds a full 16-bit value. You can go anywhere in an offset. Here we have the data path for the load with the PC relative addressing mode. You can see the 9-bit sign extended offset, which is embedded in the instruction, gets added to the program counter to calculate the value for the memory address register. The memory address register then points to that value in the memory, and the contents get copied to the memory data register, which then get written to the destination register. Store works the same way, except we're moving from the register, the source register, to memory. So it's going backwards, if you will, or the other way of load. So the value from the source register is copied to the memory data register, and then to calculate the target address out in memory, we take the program counter and we sign extend the 9-bit offset and add that to the program counter, and that is written to the memory address register, which then points to the address in memory where we're going to copy the value in the memory data register, which came from the source register. The content presented in Chapter 5 is very significant and will be used extensively in the rest of this class. So I've decided to break it up into 2 parts. This is the end of part 1. Of course, if you have any questions about any of this, please don't hesitate to reach out to me. It is important that you do the hands-on demos that I've embedded in this, and that you ask questions so as to not move forward with any unanswered questions or concepts you don't understand. Thanks for watching. Have a great day.